Hello and welcome to your first video lecture for Chem 371 of 2019. So this video lecture is going to talk a bit more about capacitors than what we had time to get through in class. Just to remind you, we're talking about a circuit that I'll draw it as an open circuit to begin with, has a capacitor in series with a resistor. And so we can think about current that might flow through this circuit, and we can think about the voltage across the capacitor and the voltage across the resistor. And at the moment that we close this switch, the current initially spikes and then drops off exponentially as the charge builds up on the capacitor. So current is flowing this way. So that's the shape of I. I'll just label this magnitude versus time. And the voltage across the resistor, of course, takes the same shape as I because we have this relationship for the voltage across the resistor between the current and the resistance. At the same time, the voltage across the capacitor starts out at 0 and exponentially approaches the supply voltage. And the relationship between the amount of charge, which we denote with Q, stored on the capacitor, and the voltage applied to it is just determined by this proportionality constant, the capacitance C. So now that's where we got to in class. Now we're going to look at the time dependence of the charge on the capacitor as a function of time. So to do that, we're going to take the derivative of both sides of this equation with respect to time. So now I'm using lowercase letters for the charge on the capacitor and the voltage across the capacitor because I'm talking about something to distinguish variables that are instantaneous values rather than equilibrium values. So these are equilibrium values when the circuit has fully charged the capacitor and current has stopped flowing, and these are instantaneous values that might be at some other time that's not at equilibrium. So if we take that equation and we look at it, we note that this has units of charge over time. So this is actually just I. So we have I equals C times dVc dt. So now we need to think about the voltage and how it's responding over time. Exactly what determines the shape of these curves. So when we're thinking about the voltage, we have the supply voltage, and that equals the sum of the voltage across the capacitor plus the voltage across the resistor. So the voltage across the capacitor is driven by this equation. So that one is Q little q over C, and this one is I times R. So I'm using lowercase values here. Again, this is the instantaneous charge that has been stored at whatever moment we're at, and this is the instantaneous current that is flowing at whatever moment we're at. So that is how we write those voltages. Now we can again take the derivative of this equation on both sides with respect to time. So dVs dt is 0. Because it's a power supply and is constant. So then dq dt over C, because C is a constant, so we don't have to worry about it with taking the derivative. Oops. I dt times R. So again, we have this quantity charge versus time that is I. So we can write this as I over C plus di dt times R equals 0. So we can rearrange that to di over I equals negative dt over RC. And you can pause the video and convince yourself that this does rearrange to that, but we'll just take that as the rearranged equation, and we will integrate both sides. So when we're integrating, we have the integration from I init to some current at some moment, and in time we're integrating from time 0 to time t. So the negative sign is out here. And the I init is the spike that we see. I init is the spike that we see in the current just at the moment that the circuit is closed, and so that is time 0. So this is the equation we're integrating, and I'm going to need a new page now, so we'll take that away. But the integrated circuit equation then is, well, okay, I'm going to rewrite it. So when we integrate that, we wind up with the natural log of I evaluated from I init to I equals negative t over RC evaluated from 0 to t. So then we can write I equals I init times e to the negative t over RC. So just like we had drawn the picture before, this shows us that I will initially spike to some value, some value that we'll talk about in a moment. And then it decays exponentially with time. So what is I init? So at the moment that we have just closed this circuit, we always have Vs equals Vr plus Vc, but Vc is 0. So no voltage has had a chance to build up there because we have just begun flowing current. So we can relate so at that moment, the supply voltage equals the voltage across the resistance, which equals I init times R. So I init times R is the voltage supply, or I init equals Vs over R. So now we have a function of values that we know to allow us to calculate what the current is at any time. So now we want to look at the voltages as a function of time. So to calculate the voltages, we have Vr at any point in time is determined by the instantaneous current that is flowing times the resistance, which is a constant, and the voltage supply equals Vr plus Vc. So now we have the voltage across the resistor that we can determine based on our ability to calculate I at any moment in time, and then that allows us to calculate V sub c as a function of time as well, because we have this relationship between V sub r and V sub c and V sub s, which is constant. So we have V sub r, that's the easy one. That's the first one to do. So we're just going to substitute in this value for I here. And I'll note that I init times R is just the voltage supply. So that is Vs e to the negative t over Rc. And now we have an expression for V sub r as a function of time and the voltage supply. And so now we can solve for V sub c. So we have V sub s equals Vs e to the negative t over Rc plus V sub c. So just rearranging and then factoring out the V sub s. So now we have expressions for the voltage across the capacitor as a function of time, the voltage across the resistor as a function of time, and the current as a function of time. So those are the three main equations that determine the behavior of the circuit with the capacitor in it. So now I'll just give you one practical example. You'll also get to play with capacitors in class. So one common thing that is done with a capacitor, as an RC circuit, is that you can make something called a high pass or a low pass filter. So let's imagine that instead of having a voltage supply, I now have some signal that's coming in that's varying in time. And I'll draw a picture of what that signal might look like. So let's say you have some spiky stuff. And you also have sort of an underlying periodicity that's going on with your signal. So now we can imagine what happens across V sub c and V sub r. So V sub r is going to pick up all of these instantaneous little fluctuations, because as this source changes, it's going to push the current, it's going to be constantly trying to drive this V sub c towards the value, the instantaneous value that's coming in from the signal. So if we measure the voltage across this resistor, so this is the incoming signal. So if we measure the voltage only across the resistor, we get only the short time variability signal. And we dampen out or we get rid of all of this underlying sinusoidal behavior because the voltage on this end hasn't had a chance to equilibrate to any of those at any moment in time. So this is called a high-pass filter. So that would allow you to have a signal coming in where you wanted to ignore these fluctuations and only find the small scale ones, and then you could measure those. Similarly, if you measure the voltage across the capacitor, that will give you only the slow time varying ones. And so that we would call a low pass filter. And so that is a really commonly useful thing in a lot of signal processing and instruments that you might be interacting with.